Okay, so we're going to continue with our relativistic mechanics, and we're going to think about the mass-energy relationship. Okay, and to do that, we're going to consider the inner product of the 4 velocity, v mu, with the 4 force, f mu. Okay, and if you remember, the 4 velocity, v mu, is equal to gamma c and v, the 3 velocity, and the 4 force, f mu, is equal to gamma c dm by dt, and then the 3 force f. Okay, so we're going to think about this inner product. Okay, so we've got a gamma squared, gamma times gamma, and then we've got the first component with the first component, and remember the first component of our metric has a -1, so this becomes minus c times c, which is c squared dm by dt. And then we've got the spatial components with the spatial components with a plus from our metric. So this is plus f dot v. Okay, so this is a number. Okay, it's one number plus another number. And yes, to proceed, let's also think about f of mu as being dp mu by d tau. Okay, and p mu here is our 4 momentum. Tau is the proper time. This is equal to m0, the rest mass. So p is m0 v mu. So this is d by the proper time of 4 velocity mu. Okay, and this equals m0 d4 velocity by d tau, which is just the 4 acceleration. So it's m0 4 acceleration. Okay, so that means that we can also write the inner product f of v mu and f mu as m0 v mu with f mu. Okay, now it turns out that the 4 velocity and 4 acceleration are orthogonal, so this equals 0. Okay, and it's a good exercise for you guys to show that. Okay, but if this equals 0, then this thing in the brackets equals 0. So this implies that we have c squared dm by dt equals f dot v. Okay, now f dot v, this is the rate of work done on the particle. Okay, so it's the power, it's the rate of change of energy done by a force F acting on the particle with velocity v, instantaneous velocity. Okay, so we can integrate this, and we get that c squared, so we integrate with respect to time. So we have integral dm equals the integral of f dot v dt between two times, like say t1 and t2, and this is m1 and m2. So this means that m2c squared minus m1c squared equals the rate of change of energy. Okay, t1, t2, f dot v dt. Okay, and at this point we can define kinetic energy. So kinetic energy, and it's defined as the energy required to bring a particle from rest up to its current velocity. Okay, so let's call it T, and the kinetic energy is equal to m, the mass of the particle, c squared, minus the energy it had at rest, okay, or the energy So we're considering, so this mass depends on velocity, this mass depends on velocity. If m1 we take to be at rest, then we've got m and an m0, so the mass and the rest mass. Okay, so m is equal to gamma m0, so this becomes gamma m0 c squared minus m0 c squared, which equals gamma minus 1 m0 c squared. Okay, so our kinetic energy, T, is gamma minus 1 m0 c squared. And you'll see that if you take the limit that V over C goes to 1, then gamma minus 1 will give you 1/2 V squared over C squared, and you'll get the kinetic energy as a half mv squared, as you always expect in classical mechanics. Okay, but this is kinetic energy defined more generally according to special relativity. Okay, so both this equation that is circled and the kinetic energy one, they relate a change in energy to a change in mass. Okay, and Einstein then postulated, he had the insight to think that, well, if a change in energy results in a change in mass, or a change in mass results in a change in energy, then maybe every particle can get rid of its rest mass, or every rest mass can be equated with energy. Okay, so Einstein defined the energy of a particle, E, as the kinetic energy plus m0, the rest mass, c squared. Okay, and we call this mc squared. Okay, and we can just check. T is gamma minus 1 m0 c squared. We've got another m0 c squared. Okay, so this mz squared is equal to gamma m0 c squared. Okay, so we know that the rest mass m0 times gamma is this relativistic mass m. Okay. Each particle has an energy E equal to mc squared, where this m is the relativistic mass given by gamma times the rest mass. Okay, and this is an amazing result. So starting from just considerations of space and time and the constancy of the speed of light, Einstein was able to postulate that mass and energy are equivalent, okay, and related like so. Okay, and this has been verified experimentally through, for example, the annihilation of matter with antimatter. Okay, but in many places. Okay, so this is true. Okay, so with E equals mc squared, and this is gamma m0 c squared. Okay, so m is gamma m0. We can think about our forward momentum again. P mu is equal to mc p. Okay, but now we know that mc is just E over c, so it's usually helpful to write our forward momentum as E over c in the first kind of time-like component, and then the three momentum p. Okay, so let's think about the length of our forward momentum. It's the inner product p mu. Okay, and this equals minus E squared over c squared plus p squared. Okay, and this is the modulus of the three vector momentum. Okay, so this is minus E squared over c squared plus p squared. This is just a scalar quantity, okay? So p is just a number. Okay, so this thing is a 4-vector inner product, so this is invariant. Okay, so this thing is also invariant. Okay, but we can think about P mu as m0 v mu, the forward velocity. So this left-hand side, P mu becomes m0 squared v mu. Okay, and the inner product of the forward velocity with itself is just minus c squared. So this is minus m0 c squared. m0 squared c squared. Okay, so we found that this must equal this. Okay, so we've got minus e squared over c squared plus p squared equals minus m0 squared c squared. Okay, if we take e to the right hand side and bring the m0 to the left hand side, we get that we've got a very important result. E squared equals m0 squared c to the power 4 plus p squared c squared. Okay, so this is an extremely important result, and it tells us that the energy of a body squared can be worked out as its rest mass squared times the fourth power of the speed of light. This is a huge number, plus p squared c squared. Okay, so E equals mc squared, where this m is the relativistic mass. M equals gamma m0, so the gamma factor times the rest mass, or the square is related to the square of the energy is m0 squared c to the 4, and then this is the magnitude of the momentum squared, c squared. Okay, so these are important results, and we'll use these and the conservation of energy and momentum to solve some collisional problems. Okay. Okay. So you can see that if you've got zero momentum, then E is just your rest mass c squared. Okay. So as you gain momentum, you gain some energy, and your mass increases.